What's up, guys? The reason I do this video is because I'm kind of interested. Lately in my feed, for some reason, I've been getting, what do you say, like, flat Earth videos. And I was seeing, like, people explain, to the flat earthers, to the, explain that the Earth is a globe. So, I know a little bit of Roblox Studio. You guys know that. So, maybe I was thinking, it's like, you know what? Maybe I could do a little model with this. I could do a little model, a little observation, a little keen observation with explanation on the Earth, the Sun, and the Moon, how eclipses work, and stuff like that. You know what I'm saying? So we could do something like that. So right now with a normal base plate, I'm like a normal base plate. So what we could do is remove these things. Remove these things. Give a space background, an awesome space background. Look right here. This just kind of look like space. Okay, let me make the let me make the sun, earth, and moon. Okay, so now we have the sun, earth, and moon models. So see, like I gotta go in closer. See, like we got the moon. Oh, but that's bright. Well, the brightness to 0. You know what I'm saying? Sun should not. Oh, what the? What's the moon doing there? Let's do. Yeah, okay, let's do this thing. 0 and 0. Bam. That should fix it. Let's do that then. Okay. Since we have a little bright side here. So this is our Earth. In this Earth. So right now, since it's on a straight line, there should be an eclipse happening. So if we go on Earth's surface, are they even in a straight line? No, they're not. It's like a partial eclipse. That doesn't look like an eclipse. Let's fix that because they're not accurate right now. It's not accurate right now. So with our awesome conversion botinator, we can do this. So the Earth is 4.9 billion. Yeah, it's 4.9 billion meters. That's a lot of meters. That's a big planet. That's a big planet. So, if we scale it down to 1/50th scale, the Earth's diameter is gonna be 246 meters. Roblox studs are 0.28 of a meter. So, if we divide, I have my trusty calculator for this. If we divide 246 divided by 0.28, we get 878. So our Earth model right now is not 800. It's 200. So let's do 878. That's a 1/50th scale. Well, I might have to make it smaller. Low key. How about 1? Yeah, that's good. That's a bit too big. Let me make it a little bit smaller, because we're also gonna have to like modify the size. Let's do 1/100th scale. 492. Okay, 492 divided by 8. Oh, 1 ton. I did it differently. I'm using this cool scale conversion calculator. That converts the Earth. I did it. I converted 4.9 billion to 1/100th scale, to a meter in 1/10 scale. So now the Earth's size is gonna be 29.2 on all of them. Okay, I gotta lower everything here. Actually, since we're still talking about Earth, we could do the layers of the Earth. So yeah, we could do that. We could do that. Since the center of the Earth is molten iron, I think. Well, molten iron, I think. It's a solid inner core. Oh, never mind. I was wrong. Whoops. Future Guac here. I went to correct my correction here that says that the Earth's core is not molten. It's solid, and it's made out of iron and nickel, not just iron. So that's my bad. Good thing I caught myself. Okay. So neon. I'm using a Google image for this. Too lazy to actually remember this from school. So we got the Earth here. I mean, if we're trying to make an Earth model, we gotta make it accurate, man. There we go. Yeah. Oh, yeah. Okay, this is awesome. Okay, and then this is... We can rename this as... We can rename this as continents. And then... In position, bam. Oh, crap, this is too big. We could just... Lower it down a bit. I know it's not like... Oh, to scale, to Earth. No, it's not. I know that. This doesn't look exactly like Earth, but I know. But it's an Earth representative. There we go. We have some land masses. Yeah, that's gonna look like the world of One Piece, but it's crazy. Okay, there you go. We have some land. And those continents with some lakes and stuff. There you go. And that's the Earth. Oh, can't forget about the atmosphere. And then a thin layer of atmosphere. So look. This explains why the skies are blue. So what this happens is how the skies are blue and then on sunset it turns red is because of the atmosphere. So what it does is the light of the sun goes inside the Earth. So we could draw here, example. So what the sun does is that his sun rays go all the way here through Earth. But since the Earth has an atmosphere, it like diffracts. So you know how you put a straw inside of a water, you see like the straw, like at an angle, you see that the straw has like a little shift. That's, I think, refraction. That's refraction. That's refraction. The atmosphere works as the same thing. So when the light goes here, it like bounces off, it absorbs, it bounces off the red and yellow. I think it bounces off. Okay, in our atmosphere, like lights are separated as wavelengths, right? So blue to all the way to violet, they are short wavelengths. The red and orange, red to orange, so your red, yellows, and orange are longer wavelengths. Your green, blues, and violets, there are shorter wavelengths. So during the day, like in the afternoons, the longer wavelengths get nulled out by the shorter wavelengths, henceforth giving you the blue skies. But during sunset and during sunrise, the shorter wavelengths don't have a lot of chance to scatter around, giving more opportunity for the longer wavelengths to chillax for a bit and reach us to our eyes. Reach us in our eyes, giving us the sunsets, the red sunsets, or the orange sunsets. So yeah, that's cool. That's kind of cool. That's why we see those colors shifting. And that's how lunar eclipses also are red. That's why the moon on a lunar eclipse it's red. Why? Because what's happening is that when the moon is right behind Earth, let's move the moon here. Oh, it's not even. Okay. So when the it's not up to scale right now. Let me fix it. Okay, so when the moon is right behind Earth, so what's happening is that the lights go in, but they curve around the Earth because of atmospheric refraction, and they go towards the moon, and then the moonlight bounces off the sun, so it gets bounces off. But since it's so perfect, we get that little area where the sunlight, instead of being like the sunlight gets only like the red wavelength, and that's how we see the moon red. That's how we observe the moon red on a lunar eclipse. When it's still white, the color doesn't change. It's just how it basically gets like a little red tint on it. In a nutshell, that's how it is. You can Google search it. I could be wrong. Okay, now let's convert the moon. I just look metallic. Oh well. There we go. Earth. Oh wait, we gotta weld all of these together. Now the sun. Size of sun. Holy smokes, that's huge. That's really huge. Look at this. E to the 9th. This is what we're gonna have to convert studs, bro. So I think this might be more. Yeah, 2048 might be a safe guess, safe assumption. Okay, now let's move 53.4 billion studs. We can't do that. Let's do this. So let's just reduce here. Let's just go to 53, 428, and 571. Yeah, it's in a null. Yeah, it's getting nulled. Let's do around here. The Earth model, of course. Now, the moon. You can fit the whole solar system in the moon from, like, if they're back to back. So we can get, let's do 800 studs. That seems really far. From the Earth, Sun, and Moon. That seems really far. It's a scale model, so it's not up to scale. It's more like a demonstration. So I was trying my best to make it up to scale and accurate. But if it isn't, then that's fine. Okay, so from the sun, it was how much? Again? 607.73. Okay. That's the distance. The speed, we can do it 1,000. And then from the moon orbit, Earth, we can do the speed 10. And the distance is 80. So from our perspective, we can add the ISS. The International Space Station. Let's see if we can find any internet. I'm too lazy to actually. You know what? I'm gonna make one. Okay. So let's pull up a reference model of the ISS. It includes one script. Okay, I do not want that. Okay. 1, 2, 3. Let's make our own model. Holy smokes! Just to. Okay. Okay, this is actually kind of sick. Okay, let's see. Oh, this one barely pokes out. Okay. Oh, so this one's the tallest point of the International Space Station. Okay. Now we go a little bit taller. And then we do it with a slightly darker gray since it's an extension of it. Bam, International Space Station. Bam, International Space Station. Looks so beautiful. Okay. And we union all of this together. It stays in one piece. And then we call this ISS. And then right by the Earth, let's do its orientation 0, 0, 0. Oh, wrong side. Okay. So compared to Earth, this guy is really, really, really. Look how small this is! Look how small this is compared to the Earth. Actually, might be even smaller. Yeah, okay. So, from what we know here, is that this little guy is way smaller here, and it's at this little angle right here. 140 degrees. Oh wait, I have to weld this to Earth. Wait, no, I have to do the continent. Weld that to the continent. Okay. So, the International Space Station would also have its script. Its moon orbit script, because it's basically a little moon. Okay. I think I spelled it wrong. Okay. Distance shouldn't be 180. It should be from the Earth, which is the position. Let's see. 33. We're just like right outside Earth. So, yeah. Like right here. We're right outside the thingy from Earth. So, dude, we're not even close to what we call space, man. We might be even closer to the... Yeah, that's how close we are to Earth. Compared to space. So the distance is not 80. Could be like 34. Let's do space. Let's do close. And then the speed could be like 5. We gotta add a highlight to this. small speck of a dot. That's how small the ISS is. And we're even smaller. We're even smaller. Dude, that's how big the Earth is. Like, and this is why we can't see the curvature of the Earth. Why? Because in this scale, we're like this small. Like this small compared to the Earth. Like here, you could still see the curvature, but there we go. See, look, I'm right now standing on Earth, but we can see the straight line here. We can see the straight line. I'm standing on the Earth. I'm standing on it. Like we're even smaller. We're like smaller than the ISS too. We might even see like a straight line. Just because we see the straight line, like from here to there, doesn't mean that the Earth isn't flat. It's round. Like, it's round. It's round. Okay. So this is how the Earth is orbiting the sun. The Earth is orbiting the sun. Although the Earth is orbiting the sun, the moon is also orbiting with the Earth. I think we gotta to go a little bit slower. 0. Let's do 5. Now distance could be 173. Then the satellite could be a angle of 23 degrees. And the speed could be 0.00051. Then we see the okay. Let's make the Earth a little bit slower so we can see the Earth's moving. It's moving at a very slow rate. So this is the moon. This is how the moon is going around the Earth. Like slowly but surely, but that's how you see the phases of the moon. We could do. Where is the International Space Station? Oh, there it is. I couldn't even see it from space. So yeah, that's the International Space Station just moving, cruising around along the Earth. Cruising. He's just cruising like this. Look at him go. Yeah, compared to this, like we're seeing nothing, man. And the fact that from the distance we can see the light of the sun. Like this is insane. Like there's this is like a small demonstration, but there's gotta be no. Oh, what if we add clouds? Like a cloud decal. Let's see if there's any Earth models. Okay, now this is starting to look like a habitable planet. Okay. And then we can give it its rotation script here. And then we could weld it. Cloud layer, we can give it its rotation script here. Wait a minute. It's a 0.25 tilt. Forgot to add the tilt. Okay. So the Earth is tilted 25 degrees. Not 25, it's 23. It has a 23-degree tilt. So that's how seasons happen. Why? Because there's a northern and southern hemisphere. So right now, southern hemisphere is pointed directly, like it's closer to the sun, meaning it has a summer, which is in summer. The southern hemisphere is right now in summer, and the northern hemisphere is in winter. Sun also rotates. Where is the International Space Station here? But yeah, this is like really cool. This is really cool. Okay, so you see, the sun is facing here to this Earth right here. So this side of the Earth is daytime. This side of the Earth is daytime. This other side of the Earth is nighttime. Like facing it away is nighttime. That's how day and night cycles work. When this side is in front, because it's rotating by itself, I think Roblox can't handle like it moving from one side to another while rotating by itself. I think the Roblox engine can't handle that. Okay, let's run that now. Okay. This is how it's going. Oh, okay. So it's moving and the moon doesn't go too fast either. So moon orbit, let's do moving slightly faster now. Okay, okay. So yeah. Where's the trail? I added a trail here. So you see how the moon is moving with the Earth. That's how moon cycles happen too. So when the moon is in front of the Earth and it's in between the sun, that is a eclipse or a new moon. But depending on the moon too, depending on the moon. Okay, so how what I said before was like about the moon being in front of the Earth being a new moon. Yeah, that stuff is true, but like it's also that since the moon, I think further on I explained how the moon orbits in an angle. So it's only in the perfect conditions is where we get a total solar eclipse, where the moon is in front of the Earth and be like in front of the Earth, but behind the sun, like what we're facing, creates a solar eclipse. That's a solar eclipse. When the moon is behind it, it's a full moon. But if it's in the perfect conditions, it's a lunar eclipse, total lunar eclipse. So yeah, I think I go on and explain about the angles, but I just wanted to let that clear. Like the moon phases also mean like where the sun is facing it. When the moon is in front of us but behind the sun, that is a new moon. We don't see anything in the sky. When it's behind us, it's a full moon. That's where the sun is reflecting the light off of it. So that's how we see it. Any other position, we get waxing or waning gibbouses, waxing or waning crescents. That's where we get our moon phases. It's just how the light is bouncing off of the moon. I need to see if the moon orbits the Earth in an angle. Oh, it's a 5-degree tilt. Okay. Moon orbit, the angle, it's 5 degrees. Since it's a 5-degree tilt, now we see I think we can see the tilt here. Okay. There you go. We see the we see the tilt of the Earth, Sun, and the Moon. That's how it orbits. That's how it orbits. That's how it orbits around the sun. Like I don't know how uh people imagine flat Earth like this. Also, I also seen like some flat earthers do like talk about biblical Earth, about the egg and the turtle. No, dude, biblical Earth is round Earth. Like I think I could pull it up right now. Uh like it talks about how the Earth is round, suspended over nothing. And when it talks about nothing, it's suspended over nothing in the vacuum of space with the gravity of the only thing that's holding it together is with the gravity of the sun. Like here is proof that like this is a functional system. It works. Like this is also how we see stars and continents in different angles from the northern southern continent too. Cause the Earth is round and it moves around the sun. And I also saw, like, I was looking, there was also a tweet about how, flat Earth, um, yeah, like, this is how flat Earth is supposed to look, this looks like. Does the sun have a point light? Oh, it doesn't. Okay, what the, where is the point light? Oh, it was me. Okay. This is the sun and the moon. And you know the sun has to emit light or else it's forever nighttime. So we need a point light. And this is how it's supposed to look like. And the thing is that for day-night cycles, for it to happen, the Earth and the Moon, the Sun and the Moon have to go like this. Like, I mean, I can kind of see it, but it's forever gonna stay daytime most of the time than nighttime. I kind of see it, but how this explain eclipses? How do you explain like different angles of the stars? Like this going around and around. As like, how do you explain the other planets in the sun in the sky? Like the other planets in their different in the night sky that you can see like them in different positions in the night sky. Like, do they all orbit around this flat Earth? Because I also saw a tweet that they say that Mars is not flat, but Earth is. So it's kind of consistent because we have Mercury, Venus, Mars, Jupiter, Saturn, Uranus, and Neptune that they're all round, and then the only flat planet we have is Earth. I don't I don't find that logical. That's how I see this. That's how I see it. Okay, I'm actually kind of proud of this model, Loki. Actually, I'm kind of proud of this model.